Hello everyone, myself Dr. Vidyanath, Associate Professor of Mathematics, CMR College of Engineering and Technology. In this particular video, we will see non-exact differential equations. In our earlier class, we have seen exact differential equations. And whenever the condition fails, that is dou m by dou y not equal to dou n by dou x, how these differential equations are solved, how the non-exact differential equations are solved, so that we will discuss. Okay, then what are non-exact differential equations? What are exact? Dou m by dou y equal to dou n by dou x. We are saying that they are exact differential equations. That is the necessary and sufficient condition for the exact differential equations. What are non-exact differential equations? So let us rewrite the differential equation once again, which is written in the standard form: mxy dx plus nxy dy is equal to 0, right? And to avoid that difficulty, we are just checking this necessary and sufficient condition for this equation to be exact or not. So dou m by dou y equal to dou n by dou x. We say that this differential equation is exact. So not equal. So whenever dou m by dou y not equal to dou n by dou x, so we say that this differential equation is not exact. So not exact or non-exact. These are the non-exact differential equations. Okay, now how to make them exact? Okay, how to make them exact? Because once we reduce them to exact differential equation, we are directly finding the general solution. That is the advantage. Okay, that is the reason we'll find out a factor which is called integrating factor. Let us see the definition of integrating factor. This helps us to convert the non-exact differential equation to an exact differential equation, right? So what is the integrating factor? So IF in the short form we may call this as, right? The purpose of these integrating factors are, by multiplying the given differential equation with the integrating factor, they will reduce the non-exact differential equation to exact differential equation. Right? What is the purpose of the integrating factor? We multiply the given differential equation with this integrating factor. Immediately, okay, the non-exact differential equation reduces to exact. Once they become exact, our condition will be true. That is, the condition is true. Therefore, we will go with the general solution. Right? So, a factor which when multiplied to a differential equation makes it exact, right, is called integrating factor. Let us see one simple example. Like we have y dx minus x dy is equal to 0. Okay. Now we have m dx plus n dy is equal to 0 form. That's very clear. Okay. Let us see what is m here. M is y and what is n value? Minus x. Now let us calculate the partial derivatives. What is dou m by dou y? 1. Okay. What is dou n by dou x? It is minus 1. So what we observe is dou m by dou y not equal to dou n by dou x. Okay. Dou m by dou y not equal to dou n by dou. Therefore, this differential equation y dx minus x dy is equal to 0 is not an exact differential equation. Now, what is our definition of integrating factor? We will find out some factor which when multiplied to a differential equation makes it exact. Now, let us consider, let the integrating factor to this differential equation, let us choose randomly 1 by x square. For example, I take 1 by x square. So, what I am saying, I have to multiply, let us consider this as equation 1. I have to multiply equation 1 with this integrating factor. So, 1 into integrating factor. So, what does this give? 1 by x square multiplied with y dx minus x dy equal to 0. Both sides I am multiplying with 1 by x square. Now, what we will get here? What is the first term? Y by x square. Y by x square into dx. Now, x by x square is 1 by x. So, minus 1 by x into dy equal to 0. Now, we got a new equation. So, once I am doing this multiplication, after doing the multiplication, I got a new equation. So, let us consider this as equation 2. Now, as you observe here, okay, this is again in the form, right, m1 dx plus n1 dy is equal to 0. Right? What is m1 here? m1 is y by x square. What is n1 here? Minus 1 by x. Now let us see whether this satisfies the exact condition or not. Okay, so we have dou m1 by dou y is how much? With respect to y we are doing, y with respect to y is 1, so we have 1 by x square. Similarly, n1 is partially differentiated with respect to x, 1 by x derivative is minus 1 by x square. Already there is a minus sign, so 1 by x square. So what we observe here is dou m1 by dou y equal to dou n1 by dou x. So what is our observation here? The second equation after multiplying with the integrating factor is becoming exact. So that is what I am putting over here. Equation 2 is exact. Okay. So therefore we will go with the general solution. I am not showing the general solution. We will see. Okay. With some examples. Right. Because already we have discussed many problems. Once it is exact, how the general solutions are formed. So our observation is here. Right. I have a differential equation which is not exact, that is y dx minus x dy is equal to 0, not exact, dou n by dou y not equal to n by dou x. Then we got the integrating factor. I have chosen some integrating factor here, right? So this is the integrating factor that I have chosen. I observed that the differential equation is becoming exact. Okay, now how you got 1 by x square? That is the question. Okay, now let me take back to the same example, right? I'll choose one more function, if, as 1 by y square. For example, let us take this as 1 by y square. Okay, so let us multiply equation 1 with 1 by y square. This is the new integrating factor that I have chosen. Let us check. Randomly I have taken this. Not always 1 by x square, 1 by y square. You can try with anyone. You can check, right? So 1 by y square. So when I'm multiplying with this 1 by y square, 1 by y square into y dx minus x dy. This is equal 0. Now what we have here, y by y square, 1 by y. Next, this is x by y square into dy. Okay. Again, once we are multiplying, we got a new equation here. So again, m1 dx plus n1 dy is equal to 0. Now for this particular part, I will get the partial derivative. So for this dou m1 by dou y, I am calculating just like the earlier case. Okay, which is minus 1 by y square. Okay, next dou n1 by dou x. Okay, for this particular term also I am calculating the derivative. With respect to x I am doing, so which is minus 1 by y square again. So they are equal now. Okay, dou m1 by dou y equal to dou n1 by dou x. Therefore this is exact. The given equation is equation 1 is exact again. Sorry, this one, equation 2 or 3. Okay, already 2 we have taken, maybe 3. Okay, so this is exact now. Right? Am I true? So what is our observation now? 1 by x square is an integrating factor to the differential equation. 1 by y square is also an integrating factor. Like that, even I can prove that 1 by x square plus y square is also an integrating factor. Like that, there are several integrating factors for the same differential equation. So the conclusion here is integrating factor, if it exists, is not unique. Okay, what is our conclusion? Integrating factors, if exist, they are not unique. There may be several integrating factors for the same differential equation, right? Now we have entered into the non-exact differential equation. Non-exact differential equations can be reduced to exact differential equation by multiplying with a suitable factor called integrating factors. Now there are various methods of solving these non-exact differential equation, because always finding the integrating factor becomes difficult. Okay, randomly choosing. That's why we were given various formulas, various techniques are available to solve these non-exact differential equations. For some of the methods, straight away some formulas are available. For few methods, right, we are rearranging the terms and we are reducing them to exact differential form. Actually, there are 5 methods. We'll discuss now the first method of solving the non-exact differential equation. In the first method, what we have? We'll look at the terms in the given differential equation. We'll try to rearrange the terms in the given differential equation. Okay, we'll look at the terms in the given differential equation. We'll try to rearrange them. We'll try to reduce them into some exact differential forms. I will show you what are those exact differential forms. Okay, what are the various formulas that are available, right? And we will solve the differential equation. Let us see that. So non-exact differential equations. Okay, method 1. Okay, in method 1, integrating factors can be found by inspection. Okay, let us see the first method of solving the non-exact differential equation. In the first method, the integrating factors can be found by inspection, right? In this particular method, we try to rearrange the terms in the differential equation, right? And we will reduce them to exact differential form. So, to find an integrating factor of, okay, m dx plus n dy is equal to 0, right? We'll make use of these various formulas that were available. Okay, d of xy. Let us see this first simple thing, right? X dy plus y dx. That means whenever you have terms that exist in the differential equation, they occur like x dy plus y dx. They can be straight away written as d of xy. This is something like uv, d by dx of u into v, which is uv dash plus vu dash, right? That is x dy plus y dx. So whenever you have this, you can straight away write that as d of xy. And when you integrate this, so we have our required answer, because the derivative integral both will are inversely proportional. So straight away xy is equal to constant, that we will get. Okay, now like this, we have few more few more formulas. D of x by y, like our u by v rule. Okay, so we have y dx minus x dy by y square. For example, if this is our right hand side, please observe. Okay, whenever we have a differential equation which exists like this, then we have y dx, that is y dx minus x dy by y square. Then this can be straight away written as d of x by y. So again, integrating the derivative and the integration, right, cancelled, and then x by y is equal to c. Like that we can have. Next, similarly, by interchanging the x and y here, okay, y by x. So what is our formula here? X dy minus y dx by x square. Okay. Next, d of x square plus y square by 2. Right? Derivative. Let us see. We have, if you want to calculate left hand side, when you observe, x square derivative is 2x, y square derivative is 2y. Yes or no? So 2 and 2 will get cancelled. So if this is the term that exists in the given differential equation, that is x dx plus y dy, then our integrating factor is, what is our integrating? What is the exact differential form to this? D of x square plus y square by 2. Next, okay, log function. D of log y by x. Okay, for example, this is our function that is to be converted, right? So y by x, already we have seen the formula, x dy minus y dx by x square. 1 by x, log x derivative we can calculate, right? So this leads to now x dy minus y dx by xy. This is the simple derivative that we have calculated for d of log y by x. So right hand side, if you observe these kind of terms, then this is our function. Okay, earlier you have seen one example also, right? Okay, with this kind of thing. 1 by x square you have seen, 1 by y square you have seen, 1 by xy is also an integrating factor for that now. Next, d of log x by y, just interchanging the terms. This is y dx minus x dy by, what we'll get? Again xy. Okay, next, let us see one more example. D of tan inverse x by y. Okay, so what is our answer? Tan inverse x derivative, we all know 1 by 1 plus x square, right? Okay, derivative, right? In the same manner, when we calculate this, this is y dx minus x dy, because again u by v is rule is applied over here, by x square plus y square. Okay, this is the formula. Next, 6, 7, 8, right? Just by interchanging the terms, okay, tan inverse y by x, because one formula if you learn, the other one you can easily understand. There is no problem in that. X dy minus y dx by x square plus y square. Okay, then like we have one or two we will take, right, because it is an extensive, right, the list is exhaust. Log xy, for example, xy already you have written x dy plus y dx. Okay, x dy plus y dx by xy. Okay, right, then like this we have d of e power x by y, for example, any particular case that arise here, which is y into e power x derivative is e power x dx, then y derivative with respect to 1, so e power x dy, then by y square as usual. So right hand side, please observe the RHS quantities of all this. In your differential equation, if you observe any terms like this, they can be straight away converted to the exact differential forms. Okay, like that the list is exhaustive. You can write any number of formulas like this, and based on our given problem, right, the simplification varies. Sometimes you have purely functions in x, purely functions in y, which can be directly integrated to obtain the general solution. So we will take an example on this first method. This is method 1, right, where the given difference, sometimes in our examinations also these are short answer type questions where they can be solved very easily just by rearranging the terms, right. Let us see one example. Okay, solve 1 plus xy into x dy plus 1 minus xy into y dx is equal to 0. Okay, so for this example, so this part is our m. Okay, this part will be our n. So just by cross checking whether dou m by dou y equal to dou n by dou x or not. So if you see dou m by dou y, this is 1 plus 2 xy, that you can work out very easily, and dou n by dou x gives 1 minus 2 xy. So dou m by dou y not equal to dou n by dou x. So therefore this is not an exact differential equation. Now we'll see what are the terms that were given in the differential equation itself, and we will try to rearrange. We'll see whether this can be converted to any of these formulas or not. Okay, for this let us rewrite. Okay, rewriting equation 1. Okay, so let us spread all those, I mean elaborate those terms. So what is the first term here? X dy plus x square y dy. Okay, plus y dx minus x y square into dx is equal to 0, right. Yeah, just a small correction, this will be m, right. Okay, and this will be n, because this is given as m dx plus n dy is equal to 0 anyway. Okay, so it's not true, right. So just you can make that correction, no problem in that. Okay, so this is actually the m and this is the n, right. So n with respect to x and n with m with respect to y. Okay, it's the same, right, anyway. Okay, they are not equal. Okay, now let us combine these two terms over here, x dy plus x square y, x dy plus y dx, because d of xy, one rule is there available for us. Okay, here the, what are those two terms? Let me change the color. Okay, this is this term and this term, will combine these two. Okay, x dy plus y dx, these two terms will combine. Next, the other two terms are here, x square y dy minus xy square dx, and from this I can take out xy common. Okay, xy if I take common, we have x left over here, x dy minus y dx is equal to 0. This is the way that this was written. Maybe there are several other methods to solve the same differential equation. We are going with this integrating factors finding in by inspection, right? Now the first two terms here, this is d of xy. That is very clear. Okay, plus let us keep this as it is, xy into x dy minus y dx. Now what I am doing here is I am dividing this entire equation with x square y square. What is the advantage? If I take this xy as a single unit, let us take xy is equal to some t, for example. Okay, so that we have, when I divide with again t square, that is x square y square, you have dt by t square form, which is now purely treated as a single unit, a function in t. Similarly, you cannot have directly xy here. We don't have any formulas that were available here. Okay, right? Because y dx minus x dy or x dy minus y dx, you have something like xy should be present, right? Or x square plus y square. Okay, some kind of those terms should be present. That is the reason we are dividing this equation, dividing with x square y square. Okay, so when we do this particular division, right? So what we'll have now, d of xy by x square y square plus x dy minus y dx by x square y square is equal to 0. I've just divided the entire equation with x square y square. Now, okay, sorry, here we don't have those, what is that? Xy is cancelled, right? Okay, because coefficient is there, xy is there. So only xy will remain. Okay, now what we observe here, I can write the first term as d of xy by xy whole square, which is something like, as I said, dt by t square. Next, x dy minus y dx by xy. We have the formula here left side as you see on the screen. Okay, d of log of y by x. So this is plus d of log of, what is that? Y by x equal to 0. Right? Now, we can directly carry out the integration here. Second term is straight away, right? Derivative integral sign will get cancelled, log of y by x will remain. And the left side, we have d of x by y, xy by x square y square. This is t square, dt by t square format. 1 by x square. What is that 1 by x square integration? Minus 1 by x. 1 by t square integration is what? Minus 1 by t. The same story. Right? Now, this leads to now, okay, integrating both sides. Integrating both sides. So this is now d of xy by xy whole square, okay, plus d of log y by x, okay, equal to some c. Okay. Now what is our answer? dt by t square answer minus 1 by t. What is our t? xy minus 1 by xy. Here integration differentiation. Right? Both will get cancelled. Log of y by x equal to c. So this is our general solution. Okay, when we solve the same problem using various other methods, it may become lengthy. Okay, even finding the integrating factors and then going with some other methods like the linear or Bernoulli, maybe we don't know whether it can be solved or not, right? Okay, so that is the reason by rearranging the terms, by observing the given formulas that were available, we can easily find out whether solution exists or not, whether that becomes exact or not. Okay, now I'll show you one more example on the same. Let us see one more example. Okay, solve y dx minus x dy plus log x into dx equal to 0. Now, as you see here, that's very clear. Dou m by dou y not equal to dou n by dou x. This is not an exact differential equation. So, when I divide with y square, for example, you have to divide this log x also with y square. Again, both x and y, both variables will be present. You cannot carry out the integration. So, I can divide only with x square. I can divide only with x square. Then log x by x square can be integrated because that is purely a function in x. So, therefore, what I am doing here, okay, dividing with x square. Dividing with x square. Very few terms are given, so no rearrangements are required. Straight away I am doing this division. So y dx minus x dy by x square, y dx minus x dy by x square plus log x by x square, okay, dx, this is equal to 0. Okay, now please observe, we have formulas available. X dy minus y dx by x square is there, right? By taking a minus sign, this can be reduced to some exact differential form. Next, here this is the second term is purely a function in x, where the integration can be carried out directly using the substitution, right? Now we have minus, if I am taking common in the first term, we have x dy minus y dx by x square. Okay, because this is directly our d of y by x from the given problem. Okay, plus Here this is now log x by x square the same. I will show you the substitution and the integration also equal to 0. Now we can carry out the integration now. This is written as d of okay, y by x. Let us see the integration part. Integrating, okay, this is integral, okay, minus sign is there, d of, how we are writing this, y by x dy minus y dx by x square, it is already there in the rules, right? Integral, here this is log x by x square dx, this is equal to c. Okay, so this is our normal integration, log x by x square normal integration. This is our exact differential condition. So minus y by x, this is plus. Okay, now here log x, when I use some substitution here, okay, I show you here this side. Okay, put log x is equal to t, right? Derivative of log x is 1 by x, 1 by x into dx become dt. So whenever log x is t, x becomes e power t, 1 by x is e power minus t. Yes or no? So here 1 by x square is there. 1 by x into 1 by x. 1 by x square is 1 by x into 1 by x. 1 by x into dx, one of them is becoming dt. Log x is t. So this is integral t. And one more 1 by x is there, which is e power minus t, right? And 1 by x dx is dt equal to c. Or, okay, this can be also written as, using the by parts for the second term, we have minus y by x, okay, plus, okay, t minus 1, t plus 1, okay, into minus e power minus t, minus of t plus 1 into e power minus t. That is our by parts rule, integration by parts, highlight formula we can use, right, equal to c. Again, what is our t value? Log x. What is e power minus t? 1 by x. So if you replace this for, or this is minus y by x, okay, minus sign is there. What is t value? Log x. So log x plus 1, log x plus 1. Then what is e power minus t? 1 by x equal to c. Or x is common for all these terms. So we have, okay, minus y, right, minus log x, right, minus 1, okay, equal to c into x, or bringing all the terms to one side. Okay, so cx plus 1 plus y plus log x equals 0. That is our general solution, obviously, right? So this is the way of rearranging the terms and then simplifying, right? So if you want, just I will leave a question for you to work out, right? You can try this example. Okay, y minus 3x square into dx minus x times 1 minus xy square into dy is equal to 0. So just work this out and check whether there is any difficulty in doing this using those standard relations that were available. Thank you.